Heat. It's what makes a cup of coffee so comforting, right? But here's the thing about heat. It's a master escape artist. It's always on the move, trying to get from hot places to cold ones. So today, we're going to crack the code on its great escape. I mean, really think about it. You pour this perfect, steaming cup of coffee, but if you get distracted, you come back and it's lukewarm. So where did all that heat go? It didn't just disappear. It escaped. But how? What were its secret escape routes? Well, it's not magic. It's just pure physics. And it turns out that escaping heat has a very specific 3-part escape plan. So let's dive in and expose every single one of its secrets. All right, first up on our list of escape routes, this is the most direct one. It's called conduction. And yeah, just like it sounds, it's all about direct touch. Okay, so the key thing to get here is that heat gets passed along kind of like a secret, from one molecule to the next. But here's the kicker. The molecules themselves don't actually go anywhere. They just vibrate in place. This is a super important distinction. It's an energy transfer, not a material transfer. Yeah, this image right here gives us a perfect visual. Just imagine this is a metal rod. You heat up one end, let's call it T1, and that energy doesn't just, poof, teleport to the other end, T2. Nope, it has to travel molecule by molecule right through the material itself. And this is basically how it works. It's a chain reaction. The molecules at the hot end get all this energy and just start vibrating like crazy, bumping into their neighbors, and then those neighbors get energized and bump into their neighbors. You get the idea. It's just like a wave of energy shooting right through the solid. Okay, on to escape route number 2. This one's called convection, and it's a whole different ballgame from conduction. This time, it's all about movement. The heat literally hitches a ride. And that's the huge difference, right? With convection, the hot stuff itself moves, carrying the heat along with it, which of course means this can only happen in fluids, things that can actually flow, like liquids and gases. The best example? Just think about boiling a pot of water. The burner heats the water at the very bottom. That hot water gets less dense, so it rises up. But then the cooler, denser water from the top has to sink down to take its place. And what you get is this constant rolling current, a convection cycle, that spreads the heat all through the pot. So that boiling water, that's what we call natural convection. It just happens because of those density changes. But you can also force it to happen. Think about a hairdryer or a fan heater. It uses a fan to physically push the hot air around. That's forced convection. Same idea, moving fluid carries heat, but a fan is doing the work instead of just physics. All right, our third and final escape route. And honestly, this one's kind of the weirdest of the bunch. It's called radiation, and it doesn't need to touch anything at all. It plays by a completely different set of rules. Yeah, this is the part that's a little mind-bending. Conduction, you need touch. Convection, you need a liquid or a gas. Radiation, it needs, well, nothing. It just travels as these invisible electromagnetic waves. It can go right through the total emptiness of space. And if you need proof, just look up. The sun. There's no giant metal rod connecting us to it, right? There's no ocean of air. Its heat travels millions and millions of kilometers through the vacuum of space, all as radiation. It's only when those waves hit our planet that we feel them as heat. Amazing. Okay, so there you have it, our 3 escape artists: conduction, convection, and radiation. So let's put them head to head. Let's see how they stack up in the great heat race. This chart really breaks it down nicely. You can see conduction is kind of slow. It's like that game of telephone. Convection is a bit faster, but you're limited by how fast the air or water can move. But radiation, whoa, it's the undisputed champ. It travels at the speed of light. And look, it's the only one that works in a vacuum. No medium required. And let's just circle back to conduction for a sec, because not all materials are the same. Metals, for instance, are amazing conductors. They've got these little free electrons that are just fantastic at zipping around and carrying heat energy. But then you've got things like wood, glass, or even just air. They're what we call insulators. Their molecules are pretty much locked down, so they're terrible at passing heat along. And that's exactly why we use them for things like pot handles or insulation in our walls. Okay, so we've dug into the science behind all 3. Now let's bring it all back to where we started and finally solve the mystery of our cooling cup of coffee. So we're back at the scene of the crime. We have our 3 main culprits: conduction, the direct touch artist; convection, the one who uses currents; and radiation, the invisible wave. So which one did it? Who's responsible for our lukewarm coffee? And the answer is all three of them. It was a team effort. You've got conduction, as the heat travels right through the solid mug down to the table. You've got convection, with the hot coffee swirling inside and the steam rising off the top. And at the same time, the outside of that warm mug is radiating heat waves out in all directions. It's a three-pronged attack. And seriously, once you see this, you can't unsee it. It's everywhere. That metal spoon handle getting hot in your soup? Pure conduction. Your air conditioner cooling down the whole room? That's convection at work. And that amazing warmth you feel from a bonfire, even when you're standing far away? You guessed it, that's radiation. These things are literally happening all around us, all the time. So I'll leave you with this final thought. Now that you know the 3 escape routes, how would you design the perfect thermos? I mean, a thermos that could keep your coffee hot basically forever. You'd have to defeat all 3 culprits, right? You'd have to stop conduction, block convection, and reflect radiation. How would you do it? The answer is all right here in what we just talked about. Something to think about.